Hey, Bryce.
Yeah. Alright, here's the lab I want to review. Because really the main part of the other day that I was really wanting you guys to get out of was interpreting graphs and how they relate.
And graphs are crazy.
And it's like taking the ACT a bunch of times, so.
Oh boy. Every class.
Position over time, velocity over time, and acceleration over time. And I'm trying to remember what it exactly looked like. Something like that. And here's our 0 level. Okay, I'm trying to think here. It was like this. I'm trying to get them to match up. Like that, approximately, right?
Yeah, it's like crazy things.
And then,
Do you know they changed that to ECG?
now I remember, if I remember right,
It was like,
the acceleration was negative, correct?
ours is flipped.
Ours was flipped.
I think ours is positive.
It shouldn't have been.
I don't remember, I guess.
Something like that, and then it was like this,
Ours is the other one.
something like that.
I don't remember. No, I thought the loops were positive and the opposite was negative.
Was it opposite? Was it a positive acceleration?
I thought
Let's
it
see.
was.
The first way would have been positive V and you're slowing down. No, that would be negative acceleration. It was.
I thought the initial peak was positive though, and then the constant was negative.
That might be true,
Yeah,
I guess. Yeah, because you're going to be speeding up. Yeah.
Where's my candy?
Yep. So, it was like that. Was this like that?
I believe so.
Actually, that's going to stay at 0. Okay? So here, I don't know if you guys realize that the point here should be, if I take it straight down, should be the point here, should be the point here. I don't know if you guys noticed that. So really, if you, all you needed to do when you were figuring out where when you were naming all those spots, you could have just done the position versus time one and then copied it on the rest.
Yeah.
I don't know if you guys realize that.
What?
They're all over the same time period. So if you know that this is the top of the peak, didn't they ask you where the top of the peak was?
Yeah.
Well, this is the top of the peak. If it's straight, same part of time,
Yeah.
straight down.
Oh my Lord.
Top of the peak. So, and let's make sense of this. This makes sense at the top of the peak because we're pretty good at position versus time graphs, right?
Yes.
What do you know about the velocity at the top of the peak?
It is 0.
0.
Let's go.
Oh, really?
Oh, yeah.
Wait, top of the.
Yeah, when you get to the, so when you pushed it up
Yeah,
before
yeah,
it went
yeah.
backwards, it had to stop, correct?
Yeah.
And what's interesting, we're going to talk about free fall today, but the acceleration was constant all the way through the top of the peak and back down. Which means when the velocity was 0 at the top of the peak, it still had a acceleration. Because acceleration can happen 2 ways. Either a change in velocity or a change in direction. And what are you doing at the top of the peak? You're changing directions. Okay. I didn't spend a ton of time talking about that. All right, so really from here, there, to, I don't know if this is going to be perfect, but you see what I'm doing here? I'm kind of shaking this all the way up. This part here and this part here, this is where your hand is touching the car. This straight constant velocity is when you're not touching the car. Because as soon as you let go of the car, when you first started the car moving, did you change the velocity really quickly?
Yeah.
Yes. And then it slowly, over time, stayed.
Constant.
Well, let me think. The change in velocity stayed constant. The velocity didn't stay constant, but the change. So the acceleration stayed constant. Does that make sense?
Yes.
Okay. So obviously, if you look at this, the velocity is changing, correct? High here, 0, went back up as it was coming down and speeding up, going back down, right? That should make sense, right? If you push it up, it's going to slow, come to a stop. It's going to speed up, going back down. But going back down is in what direction? Negative. So do you see how this would be the negative direction here? but are we speeding up? Is our magnitude getting bigger from 0 to, let's say, 2?
Yes.
No? It is. It's getting bigger. This negative 2 meters per second, that negative only tells you direction. This 2 is bigger than 0, right? You sped up. Here, when you let go of the cart, you were at your fastest speed, and it slowed down when it got to the peak, right? Yeah. Okay? But we were still a positive direction. This is positive. That's negative. Whoops.
It's also positive.
That's also no. That's negative. Okay? So this was before the peak, after the peak, but not being touched. Now notice, what is the definition of acceleration? It is the change in velocity over time. If the change in velocity is constant, you should have a constant what? Acceleration. And was our velocity changing constantly after we let it go?
Yeah.
Like every second it was changing the same amount?
Correct.
Yeah, it should have been. The only thing acting on it was gravity, and gravity is going to be the exact same thing. So every second it's changing the same amount. You can tell that by the straight line. What does the straight line tell you about the acceleration? Because slope has a big part on graphs, doesn't it? Straight slope tells us something about acceleration. You see how this is a constant acceleration? Okay. Now, was the slope of this ever a straight line?
No.
So that do we see any parallel line up here? This is a straight line, but it's not parallel. So was the velocity ever constant? The same. Was the velocity ever the same at any point in the motion? There's no horizontal line. The slope is never 0. Or constant on some non-zero number, yeah. Okay? This help. Are you seeing how all of these things were really related? So if you knew the point on the position, you should have been able to figure the point on the other stuff.
So here's the thing, if basically was just a graph of that, then yeah, but it's like the experiments.
The experiment stuff is the worst part about it.
Yeah. The 30 landed.
I agree. Okay.
Favorite is a 31. I drink 30. And I wake up.
I'm pretty sure you guys got all these equations. Okay, ignore these ones. Ignore those ones. These are the ones that I think you should have all gotten. I'm pretty sure we have this one. Yep, we have this one. We did this today in our bell ringer. We have this one, and this was that hard one we derived that one day. You don't need these ones.
It'd just be if the initial 0.
Yeah, if the initial 0, this goes away, and that's what that is. If the initial 0, that goes away, and that's what that is. If the initial 0, that goes away, and that's what that is. Okay, so you don't need to have both sets of equations, because if you plug in 0 like you should, it gives you that equation. Make sense? Okay. I think we're on that. Sorry, I'm trying to go fast. I want to make sure I get to. There's some more complicated math problems at the end of the day, so.
I want to get that
Many years. Free fall, free fall. Yes. You guys should know at least what the number for free fall is. Okay. Is there anything in our natural world that is in free fall?
No, because I have to be in a vacuum.
Yes.
For real right now.
Thank you.
Let's go.
There's no such thing. There's no such thing as free fall on Earth unless you create a vacuum. Because of air resistance. Okay. So the point is, like, if I were to drop a feather and a brick right now, which one would fall faster? The brick would. But that's only because of air resistance. If you take out the air resistance and you drop a brick and a feather, they will hit the ground at the exact same time. I'll give you this.
You did the crumpled ball.
Yeah, you want me to do that? I can do that, yeah. That one's an easy one to do.
Like if you do a rubber ball and a bowling ball, they'll still hit the ground at the same time.
Approximately, yeah. Like, if I drop this at the same time, yeah, definitely the... Oh.
That's so.
Now the surface area of this, or the fact what the wind resistance can have on this, is about the same as this. Did the mass change at all? No. Okay, so since the air resistance on both of these is approximately the same, they hit the ground at about the same time. Okay, so air resistance is the reason why things like bricks are going to fall faster than, you know, a piece of paper. But if you took the air out of it, everything accelerates at the exact same acceleration. What is that acceleration? Does anybody know? 9.81 meters per second. No matter the object in a vacuum, everything accelerates down towards the Earth at the same exact acceleration. Okay?
What?
This is all just like
maximum velocity.
not that important stuff.
Terminal velocity. Yeah, dude, I want to be like.
I'm not gonna do this. Time. All right, there's that 9.81. Okay. Technically, the reason why the acceleration on the cart experiment that we did, the reason why that was constant is because what was the only force? Well, not the only force. What was the predominant force acting on it? Gravity. Now, technically, there was probably some friction that was acting on it, but it was constant in. There was some friction acting on it. I wouldn't call it a lot. That got wheels. It's not like it's, you know, dragging a piece of wood on the ground. Okay. Now, free fall acceleration is the same for all objects. Here's its magnitude. We usually take and put a negative on that. Why?
Down.
Always going down. No matter where you are on Earth, acceleration is always towards the core of the Earth, or the center of the Earth, which is always from whatever frame of reference you're at, always straight down. Even though we live in a spherical world. Because that's kind of funny, I guess, but. Okay? So I already talked about how no matter what, the acceleration downward is that 9.81. So whether I'm at the top of the path of my cart, just going up, or on my way down, the acceleration due to gravity was the same no matter where I was. Okay? What does this tell us about changing from up to down, like at the point where the velocity is 0? What's the acceleration there?
Still same.
Still 9.81. Velocity 0. How is that possible? Well, direction changes. Alright. I know that's very difficult to understand. Velocity, this is just kind of showing you the whole sign convention for velocity and acceleration again. If I'm going up, what typically happens? Speed up or slow down?
Slow down.
Slow down. But I'm going in which direction? Positive or negative?
Positive.
Positive. So positive direction, slowing down. What do we know about acceleration in that situation? Negative. Right? It's in that chart. If you don't have that, either if you can't do that in your head or do it mathematically, you need to memorize the chart.
But that doesn't make sense.
So you want me to do the math
never
again?
mind. No, never mind.
What did you say again?
I know what you
But
mean.
then when you go down,
Yeah,
say
it's.
I said positive direction going up, slowing down, we know it has to be a negative acceleration. Okay, if I'm going down, it's a negative velocity, but I'm speeding up. It's also a negative acceleration. If you could somehow slow down going, then we would throw off the whole gravity system and probably help refute that God exists. And that
just
would
get
be
a parachute. Really good parachute.
You can't.
Really good radio.
Feel a line. A parachute with a lot of
I'm trying to think here. Is that all I need? I'm just going to. Okay, yeah, I think that's about it. The rest should be math problems.
What equation are we using for all this?
The same equation.
Oh,
Just our acceleration is constant. I did not give you any new equations. Equations?
so we use acceleration is 9.81.
Yes. Okay, did everybody hear what me and Cheyenne were kind of dialoguing about? We're still using the same equations. It's just our acceleration for free fall problems is always what? Technically negative 9.81.
So will it, like this one didn't specifically talk about acceleration, but we just.
If you look at the context of the problem, it appears that you're dropping something, and we're going to assume it's a free fall problem.
Okay.
Yep. Okay, it won't tell you, guys. In fact, it'll probably never tell you what the acceleration is for a free fall problem. It's going to assume that you know that's what it is. Everybody catch that? Okay, now we realize that acceleration is going to be a little different if we're like higher up in elevation, but we're going to assume, this is what we're going to assume. In fact, I think what's kind of funny about the fact that we're teaching, that how we teach physics, we teach it as if it's a real life class, but then we take all the real life things out of it to make it easier. For example, most of the time we completely ignore friction. almost all the time we ignore air resistance. Those are two big parts of reality, right?
When you get higher up, are there equations of factor and friction?
Can
You
you
mean,
do this one?
you mean the air resistance?
Or, yeah.
Or change in gravity? Yes.
Well, isn't air resistance?
That's pretty weird.
Yes. Air resistance is air. Yeah. So technically, air resistance is just friction.
Can
Yes.
you like zoom in and like distort this?
Okay. Let's do a couple problems.
Yeah. The negative.
It's like closing my eyes.
Okay, I don't want to get too far ahead. Any questions on acceleration from a free fall standpoint? I'm assuming it's been quite a few years. We've kind of talked about, free fall. You guys are pretty familiar with free fall. Is everybody, even though it doesn't, it's hard to rationalize it like to a perfect completion in our brain. Does everyone at a point now where they truly do believe that everything falls at the same rate?
Yes.
Sure.
Assuming we were in a vacuum.
That makes sense.
I was gonna go with
I
that.
was pretty sure that was some.
You guys, does anybody not know what I mean when I say in a vacuum? No air, so if you got no air, you got no air resistance, so the only force acting on it, when we get to forces, okay, we'll start seeing that one directional force is going to result in our acceleration. Anybody remember Newton's second law?
Oh,
No, that's the third.
That's the third.
The Fermat law.
Oh,
Force
equals
acceleration.
Your movie.
So if you only have one force, you know the acceleration. You got multiple forces. Okay. All right. Falling objects.
Yeah.
These problems will be a little bit more difficult just because of the context that we're dealing with. Okay, so pictures are good. Always label. Pictures help. Right? Jason hits a volleyball, so it moves with an initial velocity of 6 meters per second straight upward. If the volleyball starts at 2 meters above the floor, how long will it be in the air before it strikes the floor? Well, we really need to kind of have an axis here. Where was our initial position?
2 meters above the floor. 6.
No, that's
So
velocity.
this would be, what, 2 meters above the floor. There's our initial volleyball. I don't know how you do a volleyball. That's probably not how you do
That's a
it.
basketball.
Baseball. How you do a
Volleyball.
volleyball?
Volleyball's like
You have to
this.
do
It's like
3
3 lines.
It's hard.
Like
It's
this.
like a brick house, but like
Yeah, just
Yeah.
All right. I don't know how to do a volleyball, so we'll
It's
just
just
do
a
baseball.
foil.
Okay, so this is what the motion would look like. It's hard. Can I make it look like a parabola even though it's not a parabola? Because I can't, then you're not going to know. See what I'm saying?
What?
It goes up.
oh
down.
yeah, it's me.
Oh,
You can actually
yeah.
see that versus if I went over the same line, you wouldn't notice.
Yes.
But technically, it's going straight up and coming straight down because if it didn't, it'd be 2D motion. Okay.
Oh yeah.
So, my final position is what?
0.
What is my change in position?
-2.
-2. And guys, you guys understand that change in x and change in y, we use them interchangeably if we're doing one-dimensional motion. Essentially, I'm changing the y position, not the x position, but
Wait.
any change in x in your equation can also be flipped with change in
Oh,
y.
yeah. This X means displacing that Y. That Y just means like around.
Vertical displacement, x means
Yeah.
horizontal
Gotcha.
displacement. Yep.
If that's changing position, why is second?
Yeah.
But shouldn't it also go up? Shouldn't it be?
But
Oh,
it's
it's it
displacement.
and
It's the final minus initial.
Yeah, cool.
Final 0 minus initial, 0 minus 2.
because we're not.
Make sense? Okay, that's a pretty important thing, to be able to distinguish that. And it helps to draw a picture because you see, oh, they didn't land at the same spot.
Oh,
So,
wait. You flipped it to negative?
so change in x. Do you remember what change in x is?
Final minus
Final minus initial. What was my initial position?
2 meters.
What was my final?
0.
0 minus 2. What is my change in position? -2. Okay?
Why don't we do that for the other problems?
Because we didn't have any of the other problems where we were going,
Up and down. I just gave you.
where we were going, our change was a negative change.
Okay.
All our other problems were a positive change. Okay? This is the first problem we've done where we've had a negative change in position. We've had negative velocities and things like that.
Okay, so our initial velocity is 6.
Yeah.
I'm assuming the final velocity is 0.
No.
Well, usually
Oh, yeah, 'cause they make a
Well, it's essentially what is the velocity right before it hits the ground. So we do not know.
We also don't know. Okay, is that what we're searching for?
No, it's just
No.
How long will it be in the air before it strikes the floor?
Okay? And then what else don't we know? What are we solving for?
Time.
So you see what we have a two variable problem here. So we are going to need two equations to solve this problem. Unless we can find an equation that we already have that has been substituted in to solve for it.
What's changing y stand for?
It's change, it's displacement. But it's just on the y-axis.
So it's basically changing.
Change in x and change in y are the same. One change in y is just vertical, change in x is just horizontal.
So if I write change in x.
Yep, that's fine. Yep. Yep. Because I don't want you to like write an equation with change in x and then write another equation with just taking and putting change in y in it, because that'll just fill up your milk cart for no reason.
Yeah.
Makes sense? Okay? So, I don't think, if you look at your note card, I don't think we have an equation to solve for change in t
That's true.
with just these two variables. Oh, there's another variable we should know.
Acceleration.
Acceleration, sorry.
Well, that's why that's.
Yeah.
But wait, should we write it? Yeah, we should write it.
Yeah.
There we go. That makes sense.
I would.
Okay.
Always
Uh,
acceleration.
Well, T fine.
Free fall acceleration.
Otherwise,
Due to gravity, yes.
So,
Like a car accelerating in a positive direction, speeding up would be a positive acceleration.
so the acceleration is 9.81 because it's going down.
It's because the only thing acting on it is gravity. We're assuming we're in a vacuum. We're assuming anytime we do a free fall problem, there's no air resistance, and so it's not changing our acceleration.
But it's not like a person hit it. Am I just not thinking of it right?
It's like right after it hits, it's what's the initial velocity. Because when you're hit, the only time the force is on it is when it's in contact. So like right after that, it's at this speed, and the only thing acting on it is gravity.
Okay, so we're just assuming it's after the hit.
Yeah, in fact, you're going to see a lot of acceleration or free fall problems where like a ball shoots from the ground. Well, how in the world can you do that? Right? Some like going into the ground and it shoots out of the ground. No, you're just assuming that you're like throwing a ball somehow off the ground.
Okay.
If it doesn't give us acceleration, we just put that in.
If it's a free fall problem.
So we should
But
just
it doesn't
assume.
say free fall.
Well, it's a object that it's thrown in the air and it's only acting on
If
it.
it's ever just an object on there and it doesn't say there's any contact with it, we should assume it's
So yes, you may not be able to know, but it's definitely not like a car moving along the surface of the ground. It is an object by itself in the air. Make sense?
Like
Free
negative
fall.
9.81 or
Yes.
positive.
Why don't we treat it as two different like problems because it's coming down?
Why does it say positive on
Because the only thing acting on it is gravity, so it's easier just to do it all at once.
Got it.
You could do it as two separate problems, but I think it'd be more. Yeah. Okay. All right. Here we go. Let's figure this out. Since there's no problem, there's no equation that we have that has these variables and change in t without changing our VF. We're going to have to figure out what VF is first. Do we have an equation that has these variables in it that we know with VF? What is it?
VF squared equals 2a. Change in x plus VR squared.
That one? What?
Change in x plus VR squared.
I think I just moved that around a little bit, but yeah.
No, I think it's.
I think in my note card I have this and this flip. It's the same thing.
Yeah, that's the one.
And again, change in x here in the context is change in y. Okay? Yeah, just trying to make sure you understand that connection here. So we know we have A, we know we have the displacement, we know we have the initial velocity, we've got all the variables we need to solve for VF.
Damn stupid.
What's my initial 6?
36.
Positive 6, correct?
Negative
Well,
30.
either way, it's squared.
Wait,
That's
full. What'd you get?
8 times.
Did you take the square root of it?
Yeah. 8 times 6, so.
Well, I think I'm dumb.
Just for a second.
2 times.
Square go out.
Oh.
Do you get?
I got
8.6. The last square, I thought that goes inside of the six. So it's only 6. So that should just be
Yeah, it is. Oh, I did this, and still it's only the 6. Yep.
Yeah, but that's not actual.
So I do show like that to show that you technically have to square the units too. Right? You don't just square the number. You always square the unit with the number if you square it.
8.6.
Okay? You should get, when you do this, 8.7 for sig figs. And it should be, the question is it positive or negative? Because remember, when you do the square roots, it's plus or minus. We got to figure out which one it is, a positive or negative. So you think about the context of the problem, and what should it be? It should be negative. It should be negative because of the direction it's heading. Right? So we know velocity is positive up here, but at final velocity, which direction are we heading? Down, so it has to be negative. Do you see that? So for the negative, we're going to have to think about the context of the problem. In all the other classes we do, context is really not that important. This class, context is key. Just preparing you for biblical interpretation. What do we get? What did I say?
Why don't we do
8.7?
one
This is a negative 8.
timer?
I got 5.
Non-zero numbers after the decimal.
This should probably be 2.0.
Yeah.
I just didn't write it down.
Are you sure it's negative 8.7?
Yeah.
Yeah.
Doesn't matter if it's negative 8.9 or 5.
I would get 8.5.
Huh?
Did you do like the long way? Like you
I
broke
didn't
it
do
down?
Yeah, kind of.
Yeah, if you do it that way, you're probably gonna always get off a couple.
Okay.
So go, like, if you're gonna do it that way, go above and beyond what precision tells you to. Like put in much further decimal numbers than you would think you would have to, and then you should get the correct answer. Okay? Because when you do it at once, the calculator uses the big long decimal answer. Does that make sense?
Gotcha.
Okay? So that's only half of it. What else does it want then?
Time.
Essentially, we weren't even asked to solve for this, but we had to solve for this in order to figure out the time. Correct? So what equation would we use to figure out the time?
Change 2 times change in x over.
Yep.
Can we do A equals change in V over change in V?
Yeah, you can do this.
Oh, it's too easy.
I would probably use this. Just flip these two variables. So
That's too easy.
Would it be 100?
right, I'm going to get this off the bottom. It can't be on the bottom if we're going to solve for it. Bring it up here, bring A down. And so what we should have, final minus initial. Final is negative 8.7 meters per second. Minus initial, 6.0 meters per second. Divided by negative 9.81 meters per second squared.
And we are currently time traveling.
We have
1.5 seconds.
1.5 seconds, yes.
Okay. Well, I was off.
One negative.
You're currently timed out.
Question. I mean, I just use a different equation, the 2 change of x over vi plus di as
Do
well.
you get the same answer?
Yeah.
I did.
It's the same. It's also the same thing.
A lot of times you can do it multiple ways.
Oh, it's-
Sometimes you can't, depending on the context of the problem, but most of the time you can.
I got it. I don't know.
Okay? We got 5 minutes. The next one is a little bit, I think a little more challenging, but
Very true.
Initial speed.
all right, I'm actually going to make this smaller so I have more room.
It's basically just identifying the variables.
Wait,
What's
it's
every-
in a direction, so it should be initial velocity.
All right, we're going to do that so I have more room. Okay, I might keep you a little long.
I got 4 minutes before we get this.
Okay, a ball is thrown upwards from the ground with initial speed of 20. See how it says upwards from the ground? See how that's kind of, how do you do that? Just assume that the ball's starting from the ground and is starting at that speed. Okay, just randomly off the ground, just whoo. Okay. At the same instant, the ball is dropped from rest from a building 15 meters high. How long will the balls be at this? After how long will the balls be at the same height?
Oh, okay.
Okay, I read that right. So we got a ball here that is being just dropped, and we have a ball that's shooting up. It wants to know when are they at the same position? At what time?
Like 3 seconds.
No, I'm not laughing about that, I'm laughing because
This one's a tough one. So let's start with variables. What do we know?
Initial.
Okay, we got two situations here, so we need to identify VI1, VI2. What are we saying is the one? Probably the one that's 25.
Yeah.
So VI1 is 25 meters per second. What is VI2? The initial of the first guy, the initial of the second guy.
Well, which one's the first one?
So we're assuming that in the first one we read is the first guy.
acceleration of 9.81 negative.
What was that?
Why did I put the acceleration of both?
Because both go like gravity.
As soon as the ball goes up and as soon as the ball goes down, what's the only thing acting on it? Gravity. Okay? Now, we haven't done this yet, but we have an X initial and for both.
Fantastic. I love it.
What is the initial position of my first guy?
0.
What is the initial position of my second guy? And this is 15 meters above the ground, so it would be positive 15, so that's right. We want to find change in T, but we do know one other really important information. You want to know what the other really important information is?
Speed. Acceleration.
Because this is gonna, if we don't know this, we won't be able to solve it.
Finals would be, would have to be the same height.
So 7.5.
Yeah.
Oh yeah, the 7.5.
We're gonna see what I just did.
Yeah.
Well, I see it, but that doesn't.
That's when they're at the same.
Okay, so because we know, they want to know what time are they at the same height. So their final height should be the same. The reason why we need to know that is because we're going to get rid of that variable by knowing that. So here is the, I'm going to, just for time purposes, give you what the equation is we need here. And this is only the change in T is squared on that.
Oh yeah, we have that.
Okay? But I need to take this change in X and break it up into,
Oh, so then you just add changes.
And then you do it.
You just add for xi.
this is a good amount of work, guys. This is a hard problem.
Wait.
All I did is broke this up into what that equals.
They're gonna be.
Okay? Now, the reason why I'm doing this is, technically I have two unknown variables up here. I don't know XF and I don't know change in T. Do you see how those are the two variables I do not know? Do I know the initial position of both?
Yeah.
Do I know the initial velocity of both?
Yeah.
Do I know the acceleration of both? I just don't know the time and the final position. But since the final position should be equal, I can take those two equations and set them equal to each other. Here's what I mean. I'm going to take and move this over so I'm solving for XF. Plus XI. I'm going to see what I just did there. Okay, and then I'm going to take, this would be like, what is it, ball 1, and then I'm going to do another one that would equal ball 2. Let me show you what I mean. So we'll go VI1 equals the same thing but the second conditions. Which that's no easy task. So essentially I took two of these, and because I had it solved for XF, we knew that XF in both situations were equal. I substituted them in and made them equal to each other. Yes. So this would be, this here, this whole situation here would be, what, ball 1? This would be ball 2. And actually you'll see that a lot of things just cancel out and ends up being pretty easy.
I hate the VI and then having to go 1.
Wait, you just want us to solve everything.
Yeah, you would just solve at this point.
Can you give us the answer?
The answer is 0.6 seconds.
Yeah.
Is one like this one good?
That's what I think is too.
You're really smart.
Please not do that.
It was like only the positive, just like 6 numbers.
Why
Hey.
is there only one extra?
What was your homework problem? What were your home problems for today?
It was A51, 132.
Move your body.
You didn't have a problem 32,
Move
did
your
you?
body.
No.
Don't add it.
Well, that's what this problem is. This must have came from.
Oh no, that wait, that was today. Wait.
Yeah.
I don't understand the negative thing.
What negative thing?
When you just put the negative on it, and now doing the math and stuff.
Can you give me the context of what you're down about?
Oh, that's the one where I did it.
What do we mean to change it to y negative?
Let's
go. So, remember that because it's effective quantity, effective velocity each direction. That makes sense. Okay, we know the way to determine direction is by the sign of the positive number, positive direction. Negative number, opposite. Negative is down, positive is up. The final velocity is right. What is the velocity right when it hits the ground? Does that make sense? What direction will it go?
Yeah, Fisher.
Hey Mark. How are you?
It's going which direction?
Mario.
So we were going up, it'd be a positive, but as soon as it starts coming down, every point in here should be a negative.
So are you like a student here, or are you
So she's the one that's positive.
are you kind of adjusting to it? That's good.
We don't know.
Well, it depends on the speed we're going down. You will never, acceleration is the harder one from a science standpoint. Velocity is the easier one because it's just what is the direction. That makes sense?
Yes.